the problem is on Gauss theorem and charge density. These problems on the calculation of electric flux. The first problem is this one. The surface is given, planar surface, and the electric field passing through it is also given. The direction of the electric field through the plane, it is about 30 degree with the surface. Direction of electric field. The planar surface is circular in shape. It is circular surface. And here the line represents parallel to the surface, and this line represents normal to the surface, or it is perpendicular to the surface. As you know, the angle between this and this line is 90 degree. It is normal to surface, it is parallel to surface. The surface is circular surface. And the given data, the problem is electric field, that is electric field passing through the plane. Magnitude of electric field is given in SI, that is 100, and the radius of the circular surface. Radius of the circular surface is 3 meters given in SI. And we are supposed to calculate what is the electric flux through the surface. Electric flux through the surface we need to calculate. And the formula for the calculation of electric flux through the surface is, recall this formula. Electric flux is equal to E, the electric field intensity, into area of the surface, total area of the surface, cos theta. Theta means the angle between the normal and the electric field. That is not given. But the angle between the electric field and the surface is given, 30 degree. If you know this, it can be calculated because total angle is 90 degree. So this angle theta is 60 degree, it must be. Theta is 60 degree in accordance with what data is mentioned over there. E is given, magnitude of E is given, and A is not given directly. The area of the circular surface. Definition for the area of the circular surface is pi r square. Value of r is mentioned, 3 meter. That is 3 pi into 3 square. Substitute for them and calculate what we get. That is 100. E is pi r square. Value of pi is 3.143. 3 square into cos 60. Cos 60 is 1 by 2, and that is pi is 3.143. Substitute and simplify, get 455. That is 450 into this value we get the value it is, that is electric flux. Electric flux through the plane. That electric flux is, this is the magnitude of electric flux. The SI unit is Newton square meter per coulomb. It is the SI unit of electric flux to the surface. There is a geometry, that is electric flux through this geometry, a planar surface. And you see, in the second problem, it is a calculation of electric flux through a surface. The surface geometry is different. It is spherical surface. Spheres, 2 spheres are there. There are 2 spheres. Each of them is enclosing, that is charge, amount of charge. It is plus 50, it is minus 50 in microcoulomb at the center. And we calculate there is a magnitude of charge enclosed. The shape of the Enclosure is spherical shape or sphere. That is the two spheres. What is the electric flux through the surface? Magnitude of electric flux through this surface and this surface. Recall the formula for the electric flux for the symmetric surface, because Gauss law, this is Gauss law. Gauss law is applicable for symmetric surface and a symmetric charge distribution. This charge is at the center. The formula is Q divided by epsilon naught. That is flux through surface, entire surface. Total flux through the surface is amount of charge enclosed divided by epsilon naught. It is a permittivity of the free space. The value of this in SI is 8.85 into 10 to the power minus 12. Q, it is plus, it is minus. This Q depends on only magnitude. Magnitude of the flux requires only magnitude numerical value. That is 50 into 10 to the power of minus 6, because micro is not SI, coulomb is SI. It becomes coulomb. So this divided by this, calculate, you get this value. This is a magnitude of flux passing through this surface as well as this thread, as well as this surface. And what is the direction? Here minus and plus indicates the direction of the electric flux. So this is the direction. That is away, outward direction. It is inward direction. That is the only difference. Magnitude of flux remains same, but the direction is different. It is in the outward direction. It is in the inward direction. If the charge is plus, the electric flux is always in the outward direction. The charge is minus, electric flux in the inward direction. Only difference is direction. Magnitude remains same. Electric flux to surface is this is the value. Newton square meter per coulomb. This is one more geometry. This is also a symmetrical geometry or symmetrical surface enclosure. This is spherical sphere. It is a cube. Why it is symmetrical surface? The enclosure is what is that, made up of 6 surfaces. All the surfaces are equal in size and dimension. That is why the surface enclosure is symmetric. The problem says at the center plus Q charge is enclosed. That amount of charge is mentioned, that is plus 30 microcoulomb. Plus 30 microcoulomb. What is the flux through each surface? That is electric flux through each and every surface of the cube. Formula, the same formula you can apply. The formula for electric flux through the entire surface, symmetric surface, that is Q by epsilon naught. Amount of Q is this, it is given, substitute for Q, and epsilon naught in SI is this substitute, and simplify, you get this value. This value is electric flux. Look at this. Electric flux through all the surfaces, in all directions through the surfaces. But what is asked? Electric flux through each surface. Electric flux through each and every surface. There are 6 surfaces. That is the total flux through each surface. This symmetry is there again. All sides are same. Divide by 6. That gives this value. It is electric flux through each surface of the cube. Magnitude of flux passing through this. It is also in the outward direction because it carries plus Q inside. So this is one calculation, and look at this another one. It is of a different type. It is same geometry. The electric charge is enclosed at the center, but the electric charge is at the corner of the cube. electric charge is at the corner of the cube. Given the amount of electric charge, this point charge is this value, and we have to calculate what is the electric flux through each and every face of this cube. Look at this. This charge is not inside, it is at the corner. If we take at this corner, this charge actually belongs to 8 adjacent, that is 8 adjacent cube like this. So since every corner or each corner of the cube, it is equally shared between the adjacent 8 cubes, that is 1 cube behind this, 1 cube besides this, and 1 more besides this, and 4 more above, that is in the similar fashion. So this point is actually an enclosure of 8 adjacent cubes. Adjacent cube. So total flux, that is total flux means total flux due to this charge. It is the flux passing through all the 8 cubes. 8 cubes is the enclosure. 8 cube. So total flux of that enclosure is Q divided by epsilon naught. The formula, the Q value is given. Substitute for Q, and that is epsilon naught. You get this value. Look at this value. This value is the total flux. It is the total amount of flux passing through all the 8 adjacent cubes. Flux. But we have to calculate what is the flux with respect to only 1 cube. There are 8 cubes are there. Divide this value by 8. That is, one can share 1/8 of it. That is, see, this amount of flux belongs to this cube. This amount of flux divided by 8, because it belongs to 8 cubes. So for 1 cube it is the amount of flux. But one more interesting point, this point at this corner, this point is parallel to 3 planes. That is the plane above, that is the plane behind, and the plane behind this side, because parallel to, and any electric field emitting from this point always lies parallel to this plane and this plane and this plane, all these 3 planes. So electric flux parallel to the plane means no electric field emitting from this. If they are parallel, electric flux through these 3 planes will be 0. So clear? So any electric field emitting from this point is always parallel to these adjacent sides. One is above, back side, and below. So the flux through these surfaces will become 0, because electric line parallel to the plane is 0. And only electric flux through the surfaces are this surface, that is on the left side, below surface, and the front side. What is the amount of electric flux? So for 1 cube, this is the amount, and electric flux through these surfaces, that is each surface is divided by 3. It is the value, that is the electric flux passing through each of the 3 phases. That is this phase and this phase and below this phase. And these the other 3 phases, no electric flux. So look at this careful calculation, very important. So first you have to calculate what is the total flux due to this cube. What is the geometry of the enclosure? 8 cubes adjacent to this. That is the one. Divide by 8 for 1 cube, and in that cube you see that electric flux to each and every phase. Only 3 phases, that is each phase can have, that is the one. Remaining 3 phases, no electric flux. That is the one calculation. There is one important like this. That is something that what is interesting or complicated. And one more. Geometry remains same cube, but it is not enclosing any charge. Not enclosing any charge. only electric field is passing through the tube. What is the direction of the electric field? Direction of electric field is perpendicular to the lower surface and upper surface. That is the direction of electric field. And we have to calculate what is the electric flux through each surface. Electric flux through each surface. Look at this direction of electric field. Electric field is perpendicular to this surface and this surface. This is electric field. So it can have electric flux upper side and lower side. But what about the sideways? There are 4 sides. So here front side, back side, this side and this side. These faces are perpendicular to the direction of the electric field. Perpendicular to this line. So electric field, but is parallel to this plane. This electric field is parallel to the sideways, side surfaces. So if it is parallel means electric flux equals 0. So electric flux through sideways, side surfaces is 0. And what is electric flux through this surface and this surface? This surface is EA, that is area of their face into electric field. Plus because of it is outward from the surface. And what about the electric flux that is lower surface? Again perpendicular. It is inward direction. That is for inward direction this takes minus. So plus for outward, minus for inward. EA. A means same surface area. So electric flux to the upper surface, electric flux to the lower surface. Total electric flux is this plus this, because same direction. Same direction. Total electric flux is equal to simple vector addition. That is this plus this. Plus and minus cancel 0. That is 1 plus minus same value. These two are same values 0. That is one way of calculation of electric flux. So electric flux, this surface and all the surfaces is 0. No electric flux through any of the surfaces. And the other way of calculation, alternate method, is very simple. That is enclosure. For an enclosure, according to Gauss law, Q divided by epsilon naught. This enclosure has no charge but is showing electric field. No charge means 0. 0 by anything is 0. That is no electric flux. So no electric flux in any direction, no electric flux through any surface. This is another way of calculation. That is problem number 5. And next is the problem is based on electric field, calculation of electric field by what is that? Charge density. It is a linear charge density. It is surface charge density. This is volume charge density. What is the problem is given here? Here a thin wire, a conductor that is what is charging uniformly and infinite number of charges. A thin wire of infinite charges and the charges are uniformly distributed along the wire. And density of this, what is that? Linear density of this is given data, and you have to calculate what is the electric field due to this linear charge density at this point. This point is perpendicular to this line at a distance of r. The value of r is given in SI 0.12 meter. Value of r is given. And the value of the linear charge density, it is also mentioned lambda as a symbol, they have used it. That is the value given for lambda. What is that? E is supposed to calculate at this point. Recall the formula and the derivation what we did. That is the electric field at any point perpendicular to this linear charge distribution is E is equal to lambda divided by 2 pi r into epsilon naught. Lambda linear charge density divided by distance of the point from this line, a vertical distance of course. This is given. Substitute for them, and these things are constant, no values, and these things are substituted in SI. In SI. So calculate, you get the value of E. It is 2.2 Newton per coulomb. That is the electric field at this point due to this linear charge density of this value. This is a calculation. And on the problem is on surface charge density. That is, a surface is there. So it is what is that surface of, it is an infinite sheet. That is, the infinite charges are distributed and the charges are uniformly distributed. That is an area. And the surface charge density is given the data in the data problem. The surface charge density is what is that? Plus 60 nanocoulomb per square meter. Here per meter per length, per square meter area, surface charge density. That is sigma you are taking as. The surface charge density is mentioned. You are supposed to calculate what is the electric field at a point perpendicular to the surface. That is perpendicular to the plane of the surface, electric field. Recall the formula and the derivation what you did. Electric field at any point that is due to this surface is sigma divided by 2 epsilon naught. That is, sigma is surface charge density, it is given, and these are the constants, substitute for them. This value is given. We substitute for in SI. Narrow means 10 to the power minus 9. Substitute them and calculate, we get this value. This value is what is that in SI? Newton per coulomb. Electric field at a point perpendicular to the surface. The surface is what is that? It is a surface of uniform charge distribution. The density is mentioned this. And the next problem, look at this. Here we have one surface, there are two surfaces. It is just similar to capacitor. Two surfaces. Here a surface of it is that again infinite number of charges, two opposite plates facing each other. One is carrying positive charge, other is carrying negative charge, and the surface density of this, surface density of same, the given data problem, same surface density. Of course, the charges are positive charge, negative charge. The surface density is 15 microcoulomb per square meter. Surface density of this, surface density of this. Two plates of uniform, infinite number of charges. Uniform distribution, infinite number of charges. And you have to calculate what is the electric field between the two plates. Electric field between the two plates. So understand what is the direction of electric field. What is the electric field due to this plate? What is the electric field due to this plate? Formula. Direction of electric field is perpendicular to this plane. That is, direction is this. That is outward direction. What is the direction of electric field with respect to this charge? This is also perpendicular but inward towards the surface. Look at this same direction, E1 and E2. So it is the direction of electric field. So electric field due to these two plates, it is just a simple vector addition, because same direction, simple vector addition, E1 plus E2. We know that is E1, that is electric field due to this surface is sigma, recall the same formula, sigma divided by 2 epsilon naught, and it is same as sigma by 2 epsilon naught. Whatever may be the charge density is more important. It depends on charge density. So this plus this is sigma by epsilon naught. Sigma is given, substitute for them, and this is one simplify calculate. You get what is that? Electric field at any point between these two plates is this value, Newton per coulomb. Look at this difference. It is only thing there are two plates. So this concept is applicable for what is that? Capacitors. Capacitors usually made of what is that? Two plates of opposite charges, same charges, or same what is that? Surface density. This is the one problem. And the last one, it is depends on what is that? Volume charge density, that is 3 dimensions. Here the problem, according to the problem, the data is here is a spherical conductor, hollow spherical conductor. The radius of the sphere is r, and the charges are distributed, not inside. Charges are distributed on the outer surface, that is of the spherical sphere, spherical surface, 3 dimension spherical surface. The amount of charge, total amount of charge distributed on the surface is given in the problem. Q is equal to plus 20 microcoulomb, plus is there. And the radius of the sphere is mentioned as 3 meter, radius of the sphere. And you have to calculate these things, that is sigma means surface charge density. This surface is what is a 3-dimensional surface, spherical surface. What is the surface charge density? And what is the electric field at the center of the sphere? And also what is the electric field at a point, it is away, at a point somewhere around this, away from this sphere at 5 meter from the center. It is any point away from the sphere. So these things are given. Write the formula for surface charge density of the spherical surface. It is not a planar surface or any other surface. Spherical surface. General definition for surface density is what is that? Sigma is equal to total amount of charge distributed on the surface divided by surface area. What is the surface area? Area spherical. Therefore, definition for area of the sphere is 4 pi r square. R is the radius of the sphere. Given the value of r, that is value of r is 3 meter, 3 in SI, and value of Q, what is the magnitude of total charge distributed on the surface? That is 20. 20 into in SI 24 of minus because micro. Calculate this, you get this value. This value is the surface charge density. That is surface charge density on that surface. This value, coulomb per square meter. What is the electric field at the center of the space? In accordance with the Gauss law, point inside the space where there is no charges. Charges are outside. The electric field is always zero. Gauss law says. Electric field at a point in the space where there are no charges, the charges are outside. That is E, electric field is equal to zero. That is why Electric field at a point is a empty space that is outside. Electric field is equal to 0. And this is one calculated. We need to calculate one more. What is the electric field at any point in the space? The point is about 5 meters away from the center. Recall the formula and the derivation for that. So in that case, this sphere of charges act like a point charge. That is the formula for electric field at any point around it at a distance of r is k q by r square. K q by r square. What is k? Coulomb's constant. What is q? The charge that is distributed on the surface. Divided by r, distance between the center of the sphere and the point where we need to calculate electric field. Substitute for them. There is a value of k in SI is, you know that 9 in 24 of 9, and the value of q is mentioned, the same value, write it in SI. Substitute by half, that is 5 whole square, simplify, calculate, we get 7200 Newton per Coulomb, that is the electric field. So, electric field at any point around a sphere at a distance of 5 meters away from the center is, that is electric field. Look at that. The calculation of electric field due to that is three-dimensional surface, and the calculation of electric field due to two-dimensional surface, that is surface charge. Here of course volume charge. Here electric field due to linear charge density. The derivation we did and the problem we calculated. The derivation we did for the surface and the problem is calculated. Problems of this type. And the derivation we did for three dimension, that is volume charge density. It's good, but volume charge density is not asked here, surface charge density. That also can be asked. With this, we have completed this set of problems.